All right, we're going to talk a little bit about color vision today. And color vision is important, right? So can you think of some ways in which it might be important to see color? You know me, I'm going to go back to the evolutionary kinds of explanations here, right? So being able to differentiate objects in the environment based on color, those that could do it and those organisms that could do it and found it some benefit from that developed that ability and passed it on to their ancestors, right? So being able to spot berries of some red or blue or purple color or whatever among green leaves was probably something that was advantageous. Evolution works in ways that are effective, right? Not necessarily optimal. There's plenty of light that we can't see as humans that other species can see. For example, bees and birds can see ultraviolet light. It wasn't very useful for humans, and so it didn't evolve. So what is color? Color is not a characteristic of an object, even though it appears that way to us, right? So, if a blue balloon or a red sock or whatever, we ascribe the color to the object, but it's not. It's really the light that gets reflected from that object into your eye. So something that's red will reflect red light and absorb all the others. So what we know is that white light, sunlight, is made up of colors, of light that's all colors, right? So Isaac Newton was the first to understand this. Pink Floyd made an album cover of it. So what we're going to do here is we're going to look again at this psychophysical, physiological relationship, right? Psychophysical studies can be done to explain physiological findings. And two theories about color vision that historically kind of butted heads, right, on how it is that we perceive color. And these folks, Helmholtz and Hering, first of all, they hated each other. They were bitter rivals and kind of had traded insults in the academic literature. So Helmholtz was the father of the trichromatic theory of color vision that suggests that there are essentially three receptors in the eye that are responsible for our ability to see color. Hering was the father of the opponent process theory of color vision that said there's this kind of back and forth or opponent processes between four different colors, and kind of this is their story. First of all, they hated each other. These are quotes from manuscript articles, journal articles, peer-reviewed. So Hering said it's likely that the great Helmholtz is in his dozing state. And Helmholtz replied that he has been, as I've heard, mentally ill. So things have kind of simmered down in the academic world a bit since then. So let's talk about Helmholtz's trichromatic theory first. And remember that they're doing these experiments, these behavioral, psychophysical experiments, to make inferences about physiological structures that at the time they couldn't observe. So, color matching experiments. It turns out that if you have three different colors of light, red, green, and blue, and you mix them, you can pretty much make any color that you want, right? And so Helmholtz would bring in people, and he had these three different colored lights, and they were focused onto one spot, right? And they had three little different dimmers, right? And he would give them a little chip of color paper or something. Say, match the color on the wall to this little sample patch that I've given you. And people kind of turned the knobs a little bit and figured out pretty soon they could get it, and they could match any color. And so Helmholtz used this as evidence that all we need are these three different color receptors in the eye, and we can perceive any color there is. So Helmholtz was right? And it turns out that Helmholtz was right. So there are rods and cones in the eye. The cones are the color kind of sensing structures in the eye. The rods help you see at night, and there's all kinds of underlying physiology that transforms this light energy into a neural signal. We're not going to spend too much time on that, but to say that Helmholtz kind of got it right with respect to the three different types of receptors in the eye. Hering had evidence of after images, right? So when you're into psychology, you probably looked at this kind of transposed American flag, and if you stare at it for long enough, you get the image of the red, white, and blue flag. And he found that after images were red, green, and blue, yellow. So the opponent processes that he talked about were simply that there are cells that are red, green opponent processes. There's a balance, and if you fatigue one side, like we're doing with the American flag here, and stare at a neutral image, like a white background, the other side will temporarily kind of be more dominant, and you'll see these after image. You get the same thing with blue, yellow, and he also noted that bluish green and reddish yellow are okay because they're not opponent processes. But you never hear someone talk about reddish green or bluish yellow. And also color blindness tends to follow the patterns of red and green or blue and yellow. Personally, I can't see anything in either one of these. I have some color deficiencies. I can, not totally colorblind, but not a strength for me. Herring also had people do this sorting task. So he'd have a big bunch of these little chips of color, like when you go to buy paint, right? Just hundreds and hundreds of them, all different colors. And he basically said to people, sort them out. That was the only instructions he gave them, right? And what he found was that invariably they would sort them into kind of 4 different piles, right? Red, green, blue, and yellow. So basically Herring and Helmholtz got into a big tiff over yellow. And it was more than just a big tiff. It turns out that it elevated to a scheduled duel with pistols. It was scheduled. Turns out neither one of them showed up for it, but they didn't like each other. So we know that Helmholtz was right. Trichromatic theory was, we had kind of definitive evidence for it in the 1960s when we could measure the absorption spectra of cones and found 3 different types. One that responds primarily to blue, one primarily to green, and one primarily to red light. And people thought that was it. Helmholtz won. It turns out that they were both right. They almost killed each other over this, but they were both right. The take-home story here is when you see this dichotomy set up in the psychological literature, and it happens all the time. Do you this or this? There's a debate for both. We've got this evidence. We've got this evidence. Well, think that maybe both things could be true, which it turns out it was in this case. The evidence took a lot longer to find out because the Helmholtz kind of thought it was this kind of build-up and breakdown of chemicals in the eye, but it turns out it's a neural phenomenon that happens throughout the visual pathway, right, all the way into the visual cortex. We find these opponent process cells, so they were both right. So that's the 2 primary theories of how we perceive color. So trichromatic theory and opponent process theory, they're both right. And there are some other kind of phenomena with respect to color. It turns out that memory for color, we remember bright colors as brighter and dark colors as darker. If there's a characteristic color of a thing, we tend to remember it as brighter. So tomatoes are remembered as a brighter red. Bananas are remembered as a brighter yellow. There are in television broadcasting, for example, they enhance the color of the image that you're seeing because people complain that if they put it in real life, if they put the real color, it doesn't look like what they remember these characters or these things being. It's an odd phenomenon, but it goes to show that our memory for color is influenced by not just our visual physiology, and our color perception is not just influenced by visual physiology. There are cultural differences in how we talk about color. It turns out that there are not cultural differences in terms of how we see color. So this was the Whorfian hypothesis of color vision, right? So it turns out that in some other cultures, they have color words for red, and then a color word for everything else. So there are only 2 color words in certain cultures, right? In English, we have red, blue, green, yellow, all these other colors. And the early thinking was that this reflected perception, right? Because they didn't have a name for blue versus yellow. they had red and everything else, that people saw the world in that way. They could see red, and then everything else looked the same to them. And it was a really bad experiment, right? What are your words for it? So when psychologists, when psychophysicists, perceptual folks came into these communities to do some testing, they did the obvious test. They would say, show them something red, and then they say, what is this? And they would give them their word for red. They would show them something blue, and they would say, they would give them the word for all the other colors, right? They would show them something yellow and give them words for all the other colors. This is what this is bad methodology, right? So what the good methodology is, you say, look, are these two the same or different? And you show them red and blue, right? And of course they're going to say, well, they're different. Now the key test comes when you show them something blue and something yellow, right? If they can't see that they're different, then they're going to say they're the same. But they don't. They say, of course they're different. They look at you like you're nuts. Can't you see that they're different? Of course. But the word for them, blue and yellow, is the same. So it didn't reflect an underlying change or difference, cultural difference in perception, just a cultural difference in the language and how we call colors. That's a quick overview of color perception. Let me know if you have questions.